You may have optimized the code offline, and all you want to do is code gen it. Or you may be getting code from Clang, which does no optimization whatsoever. And so you're going to need to run the instruction combiner and other passes on that. The way we run passes in LLVM is with a pass manager, and it looks something like this. So here's some common passes that most JITs are probably going to want to run, unless you've done a significant amount of optimization offline. You see we just declare a pass manager here on the stack. Basically what it does is it enforces an ordering and makes sure that if your pass needs dominance information or whatever, that goes and gets calculated before the pass is run. It's just sort of a bookkeeper for the various passes. You say, hey, here's my target. You pass it in the module so that it knows, when alias analysis is running and you're doing crazy pointer arithmetic on int pointers, that those are really 4 bytes apart, so it can take care of that. We've got an internalized pass here, which is a really great one. If you're coming from C or you were just creating it by hand, all your functions and globals and whatever probably got created with external linkage, which is the default. The optimizers have a little bit of a hard time with that because they don't know if somebody outside the IR that they're seeing is hacking away on your stuff. So by passing an export list of this is what I'm really exporting, the optimizers can basically internalize all those external functions that you didn't care about and then delete them if they're not used, or inline them completely and get rid of them. Maybe figure out that some globals are read-only and propagate their value into all the code that read from them, stuff like that. We have a scalar replacement of aggregates pass here, which is pretty important if you're compiling an object-oriented language or you're using a lot of structs and arrays. It can break those things up so that the optimizers can get at the underlying elements of those objects without every optimization pass having to know how to dig into structs and know the target layout and all that stuff. Then we have an instruction combining pass, which is probably the most important one. And if you go and look at the various tools that run LLVM passes in the code base, you'll see people calling instruction combining 2, 3, 12 times. It is an extremely clever pass in that it knows how to convert, selects between -1 and a value into, an arithmetic rate shift and a modulo, in a leap year or something like that. But it's also really cheap, and it's a good way of cleaning up after other transformations that may leave cruft behind, or maybe the code you generated wasn't that great in the first place. And even though it takes, some non-zero amount of time to run, it usually results in getting rid of enough code that the subsequent passes run faster than it would have if you'd never run instruction combining in the first place. So if the code generator that Dan talked about knows all those tricks to get rid of DAG nodes, it would run even faster if the DAG nodes weren't there in the first place. So that's the instruction combining pass, and then you get to some IPO passes here. So we've linked these things together into our module. We've create a global optimizer pass. This is a great one for JITs in particular because it can say, I see that the internalized pass has made this function internal. It's way too big to inline it everywhere it's called, but I will change the calling convention from the standard C calling convention to my crazy fast calling convention where everything's passed in registers. It knows that it can do this because it's not external. No one outside your program can call this function. And because you're in a JIT, it's not going to live around for somebody else to call later. So basically, it can do transformations on your program specifically for a JIT that end up in noticeable performance improvements. And finally, function inlining. This is an inliner like you're all familiar with. It can, it will copy the bodies of small functions into the callers at the call site. Our inliner is relatively conservative, which is why you might, if there are functions that really need to be inlined, you might want to do it by hand. So there's also an inline function call. So you just pass it a call instruction and you say inline this, and it will do it, no matter how big it is or expensive or whether it was a good idea or not. So here's some sample code, for instance, that just finds every instance of every use of the function called inline_me in a module and replaces the call to inline_me with the body of inline_me. So pretty simple little loop. And that leaves us with code generation. So now that we have this most amazing pile of IR ever, how do we go run it and call it? Well, the JIT has two simple APIs for this. You go look up the function name in the module, it gives you an LLVM function pointer back, and then you say get pointer to this function. And what the JIT is going to do at that time is it's going to say, all right, operating system, I need some memory, and go make it executable. And I'm going to then run the code generator and dump the machine code in there. And all the LLVM targets not only know what the ASM strings for the instructions should be, they know the binary encodings. So it can then go assemble all the machine code and handle the relocations and all that stuff and jam it in this memory. And then it hands you a void pointer back, which you can then typecast to the appropriate function pointer in C. And when you're done with it, you just pass free, you call free machine code for function, and the memory goes away. So, what does this look like? Were we to actually go build one of these things? Well, here's my simple little example. So I've gone and built Clang into a library, and I've made it export one function, which is C2module, which takes a C string, which is the source of my C program, and it hands me back an LLVM module back. And so here I call main. I've got get file, which is basically just a utility function that copies the contents of a file out into a C string. And I go into a loop so that we can see this happening over and over and over again. I call C to module on the source, and I get a module back. So now my module wants to call some other stuff. I want to go parse a bitcode file. So I've got my awesome extensions to libc called mylibc over here. You can see the memory buffer interface. It's just a path, which happens, so it's sitting next to my app. I go turn it into another module in memory calling parse bitcode file. So now I need to link these things together. You call link modules. It's just as easy as it looks. And we remember to delete the memory for the library since it's not valid anymore. We go get our pass manager. We register a bunch of passes. And you can see the last line here, this run. So at that point, the pass manager says, all right, I'm going to go do all this stuff. So we internalize based on the export list. We run the dead code eliminator. We run global optimizer and all that great stuff. So now we're ready to go run this code. We create a module provider, which is basically just a handle for the JIT to grab a module. We say, let's go create a JIT with this module, and give me the function, give me the pointer to my cosine, which doesn't